All right, this lecture is going to be on metamorphic rocks. This is the third and final phase of the rock cycle. We've studied igneous rocks and processes, we've studied sedimentary rocks and processes, and now we move into the third and final of the three rock types that are found within the rock cycle. We're going to be focusing on metamorphic rocks, and this implies that heat and pressure, we take an igneous rock and give it heat and pressure, it becomes metamorphosed, or we take a sedimentary rock and give it heat and pressure, and it becomes a metamorphic rock. So metamorphic rocks are formed at variable depths within the crust when pre-existing rocks, including igneous, sedimentary, and even metamorphic rocks, are changed physically and chemically due to the change of temperature, pressure, or both. During metamorphism, the texture or mineral compositions, or even both, of pre-existing rocks change under various metamorphic conditions at depth. So here's a picture we can look at. Temperature and pressure in chemically active fluids change pre-existing rocks into something new. So we use the terminology from a high to low grade metamorphism. So high grade metamorphic rocks involve gneiss, and then a little bit less high metamorphism would be schist, into phyllite, into slate, where slate would be the low grade metamorphic rock. So take a look at the conditions in which these metamorphic rocks are generated. At shallow depths and low pressures, I can take an existing shale or a mud rock, give it heat and pressure, and it becomes a slate. I can take any type of a rock pre-existing, I can take that same shale and give it more heat and more pressure, and it becomes phyllite. And notice that these pictures here are getting a little bit deeper into the earth, and there's a little bit more pressure and a little bit more temperature. So we get a different grade, and it's simply looking at the increasing of metamorphism here. So the deeper we go into the earth, the higher the grade of metamorphism. Here I'm even deeper yet. I can create schist, and schist we'll talk about all these rocks in the upcoming classes. And last but not least, we get gneiss, G-N-I-E-I-S-S. And this we get these very nice foliations here. So from low grade slate to phyllite to high grade schist to very high grade gneiss. It's simply the metamorphic grading system. So here's an example of pre-existing rocks that change due to metamorphosis into metamorphic rocks. So we can have a shale or a mudstone, right? Mudstone or siltstone under temperature and pressure turn into slate. We can have slate itself then metamorphosed into phyllite. We can have phyllite metamorphosed into schist. And we can have schist or granites or any other volcanic rock metamorphosed into gneiss. And we're simply looking at the increasing metamorphism that's taking place. Gneiss would be considered a very high grade metamorphic rock. And it'll have these very nice foliations. We'll talk about foliations as we continue to move on here. A couple other rocks that we'll be able to form. We can form marble. Marble is where you take dolostone or limestone and you heat and add pressure to them, and it creates marble. And this will also effervesce in the presence of HCl. We can take quartz sandstone and we can metamorphose it into quartzite. And we can take bituminous coal and add heat and pressure. We can form this really high grade anthracite coal. So when I'm looking at direct pressure, I'm really talking about stress. That under direct pressure or stress here, newly formed sheeted and elongated minerals such as mica and hornblende, they grow along the direction perpendicular to the compressional forces or perpendicular to the stress. So notice I have all these minerals in here, and I add pressure on the outside and they align themselves very nicely. So before metamorphism, they've got uniform stress, but after metamorphism, this is called differential stress, the resulting parallel linear alignment of sheeted or elongated minerals is defined as foliation. So this rock right here, right, this could be kind of a granite or even a diorite. But if I add pressure on either side, heat and pressure, these become foliated. So I see these very nice bands. This would be a form of banding. So this would be a nice metamorphic rock. Nice just implies it's got high grades, a lot of foliations. So there's what we call a degree of metamorphism. And these are index minerals that tell the metamorphic story. That chlorite is found, this mineral is found under very, very low temperatures, where epidote is found under this temperature range. I want you to make sure you're paying attention to the temperature range, that the lowest grade metamorphic rocks are going to contain chlorite and epidote, maybe some muscovite, maybe even a little biotite. But these also form over a large range of temperatures. So you can have biotite mica in a wide range, even in highly metamorphosed rocks. We've got hornblende, once again, not quite as large of a range as biotite. I've got sorrelite, this is a ferromagnesian, a dark mineral. I've got garnet. Garnet's typically associated with high-grade metamorphic rocks and pyroxene. So notice that my upper limits of my temperature range here, I have very commonly found pyroxene, garnet, maybe a little bit of hornblende, and definitely biotite mica. In my low-grade metamorphic rocks, I'm going to find chlorite, epidote, muscovite, and maybe a little bit of biotite. So we're simply looking at these are the approximate temperature ranges over which some representative index metamorphic minerals are stable. So we're really focusing on what temperature do these minerals exist in. Where chlorite, epidote, and muscovite appear in low-grade metamorphic rocks, I kind of went over that already. And metamorphic rocks of intermediate grade contain biotite, hornblende, starlite, and garnet. Really, your intermediate, I can just draw a line down here at about 500 plus, and I would just go 1, 2, 3, 4, and 5. So our low end, our middle range, and our high end range, where our high-grade metamorphic rocks contain pyroxene, garnet, and selemonite, but that one's not on here. So we're really looking at the different minerals that we can find. So foliated metamorphic rocks, highly foliated, here we'd have gneiss. The next level of foliation, these are both forms of schist. This is a garnet schist and this is a mica schist. And we have all these samples in our rock box. So we'll be studying over the next couple days, or at least day-ish. Here I have phyllite, and then low grade or little foliation I have slate. So these are the examples of samples that we actually have in our rock box. And then non-foliated rocks, here I have marble. Marble was once limestone or dolostone. On the right here I have interlocking grains of quartz. It has a hardness of 7 just like that of quartz. And then left I have anthracite coal. This is the highest grade of coal. It's metamorphosed from bituminous coal. And there you have your introduction to metamorphic rocks. I want to make sure you have a chance to go back and look at this picture, which was actually in your binder right here. That most of what we're doing here is just covering here. These are my foliated rocks, my foliated metamorphic rocks, where here I have slate, low grade foliation. Phyllite has a little bit more of it's a higher grade foliation, but still low grade. Here I have schist. Schist has, let's just say relative to phyllite and slate, has a lot more foliation, and gneiss has very, very clear foliations. And these are our dark banding layers here. So there you have it.